So our next talk will be provided by a startup here from the XG Mobile. The talk is NEB IoT over NTN for wildlife tracking, architecture, constraints, and early experiment plan. The speaker is going to be Mr. Daniel Matzer, who is the CTO and co-founder of Next Device. He has a master level telecommunication engineer degree. He brings 20 plus years of experience in embedded systems, R&D team leadership, innovation management, and end-to-end product development. At Next, Daniel architects energy-efficient IoT and tracking solutions, spanning hardware and firmware design, low-power wireless, and the energy harvesting techniques to extend the device lifetime. He is currently exploring 3GPP and NB-IoT over non-terrestrial networks to enable delay-tolerant connectivity for wildlife and the other remote assets. Daniel collaborates with academic and industry partners to translate the harsh environment constraints into pragmatic architecture, measure performance, and scalable deployment. Welcome, Matzer.
Thank you. Thank you, Luciano. Hi, everyone. Thank you for being here. My name is Daniel Matzer. I'm CTO and co-founder of Next Devices. Next Devices is an R&D company focused in embedded systems and also in connectivity. And today I'll talk a little bit about a product we are developing. It's a tracker for wildlife marine animals. And we are using NTN, non-terrestrial networks, like for the communication with this tracker to the end application. The content of the presentation is just in the title of the slide. I'll talk about the architecture of the tracker that we are developing, our constraints, our early experiments plan, and some results that we already have. The product, it's not already done. We are in the process of development. So we have a lot of open questions yet to answer. So this is what I will show to you today. Okay, so why do we need to track animals using satellites? So most of our planets are covered by oceans. So if we need a reliable data, if we need to collect information about the animal, the marine animal in their natural habitat, we need to rely on satellite communications to acquire this data from these animals. Also, conservation management depends on long-term data. So it's not completely reliable to collect the data only when the animal is near of the shore. It's very important to collect the data when the animal is also far from the shore. So satellite is like a very used technology for this, and we think it's for our application, it's very essential. This picture, as you can see, it's the animal that we are going to track in the first version of our device. This is a manatee. It's a peixe-boi in Portuguese. And what we are seeing is just the nose of the peixe-boi, of the manatee. This is one of the moments that they go to the surface to breathe. And this is one of the challenges that we have. My talk roadmap will be this. I will talk about satellite communications and for constrained devices, then the marine tracking context in the side of the Navi project that we are participating, the manatee tracker architecture, and how we are going to place NTN on this device. And in the end, a little bit more technical slides, system architecture, hardware modules, the connection flow in our first results with the NTN. So let's start with what it's a constrained device for our application. This is a manatee, and this is a tracker. the tracker is attached to a cord to the animal, near to the tail of the animal. So for the engineering point of view, we have some constraints. One of the most important is the size of the equipment. They not be large. So we need to deal with the small device. We need to develop a small device. And when we develop a small device, we have small batteries. So we have a very, we have a very severe energy budget to deal with. Also, as we will communicate with satellite, we need to understand that we will have a very low bit rate with limited data packets, and we need to tolerate very high latency. Our AF environment is very, very complicated. We need to communicate only when the antennas are outside of the water. So we need to provide a ways to detect when the antenna is outside of the water. And also we need to develop a solution that is reliable and have a ruggedness in real conditions in marine environment. Then from a researcher point of view, we also need, the researchers also need a tracker with simple deployment and long-term operation. So the deployment of this kind of device in the animal is it's danger, it's stressful to the animal. So we need to develop something that it's easy to attach to the animal and keeps in the animal for a long period of time. The researchers don't need to recapture this animal to replace batteries or to make kind of maintenance. So this is one of the requirements. Also, they need adequate spatial and temporal resolution. They need that data with adequate intervals of collectivity of this data and with reliable precision of the location of the animals. So high tag reliability, as I said, and of course, the tag must respect the animal and does not must cause any harm to the animal. So they must be low weight, provide low drag, and cannot perturb the animal natural behavior. So what we have today of solutions to telemetry and tracking, in the 70s, it was launched. The Argo system is the first satellite constellation specific for animal tracking. And this system, of course, was evolved since then, and now they are launching a new satellite constellation, the KNICE satellite constellation. And the interesting about the system is that it already have a Doppler-based location system. So when the tracker send a message to the satellite automatically can infer what is the location of this device. So the end device, the tracker, doesn't need to have a GPS on it. And there are traditional solutions like Iridium and Globalstar satellite operators that you need to have a GPS in your device, but then you send the messages, small messages, specific for IoT and short-term communications. And you need to have your GPS in your device if you want to track it. And these solutions are very used by common players like Wildlife Computers, Lotec, Telonix. These are manufacturers of trackers. So there are a lot of models of trackers already developed, already being in the market. And there are other solutions like the VHF, where the equipment will keep sending like a beacon or a constant signal in VHF frequency, and someone can track this information. And archival tags, where these tags just store information, and to acquire this information, I need to recapture the animal, recapture the tag. So telemetry using satellite is not new. It's happening for a long time ago, so it's a mature field with a lot of players and a lot of solutions in the market. So it's a very mature field. This is an overview. This table, it's an overview of some satellite solutions. And here I'm comparing the data rate, antenna size, power use of the systems. So not including Starlink, but all the systems are are focused in small packages, small data communications, like for IoT. So what is desirable? It's desirable a small antenna. It's desirable very low power consumption. Also, it's okay to have a low data rate. We not need a very high data rate. Starlink is here just for comparison. This is a very different approach. It's a broadband satellite system for connectivity. It's very high power consumption. We need very large antennas, and but we have very high also data rate throughput. For narrowband IoT over NTN, we already have some companies that's providing connectivity. I'll talk about a little bit about Satelliot and Skylo. We also will try the Mediota connectivity in this project, but in this modality, it's not. This is the ultralight. Mediota ultralight is not an 3GPP NTN, and we will try this in our product too. But today I'll talk more about the NTN. So why 3GPP? What is 3GPP non-terrestrial network? This is an extension of all the specifications of the 3GPP for mobile communications, but adapted for satellite communications. So it was adapted for communication in space. So we can use the same protocol family as cellular. We can use the same infrastructure. My device will also have a SIM card or an embedded SIM card, but it was adapted for communication in space. So it handles long propagation delay, it handles Doppler effects, it handles that the satellite may be moving, and also device registration, that it's a little bit different than a conventional mobile phone. But the one, I think it's the most interesting part of the NTN is the possibility to have two communicating paths. So if with a single NTN module on my device, if I have terrestrial coverage of narrowband IoT, for instance, I will be able to make my user equipment communicate with a ground-based station, then with a core network, core mobile network, and then this message will reach my user application. But if my tracker goes away from terrestrial coverage, then the user equipment will be able to communicate with the satellite, then with a ground gateway that will deliver this message to the core mobile network, then to my application. So with the same communication module, I can communicate in terrestrial network and a non-terrestrial network. The NTN specification started in the release 15 and 16. It started discussed in the releases 15 and 16 in the 3GPP. In the release 17, we got the first useful, implementable features. So it formalized the new radio NTN for 5G communication over satellites, and formalized the IoT NTN. That's what we are using in our project. And in release 18 and beyond, they are still evolving. They are still planning enhancements in this kind of communication. Also, improvements in wildlife and environmental sensing. So most of the satellites operators that providing NTN connectivity are using our LEO or GEO orbit satellites. LEO, it stands for low Earth orbit, and GEO, geostationary orbit. And they have some strong differences, and this is also must be taken in. It's important to know the difference between them before we choose the satellite operator that we will use. So LEO is not so far from the ground, from the Earth, and GEO is very far from the Earth. So this reflects immediately in link budget, how much my signal is attenuated to reach the geostationary satellite. Also the round trip latency, how long it takes to my message to reach the satellite and come back to my device. And also the most important is that the LEO, it's not stationary, it's not positioned in a fixed spot. It's moving in relation to the Earth, and geostationary, it's in a fixed spot. So in our use case, where I have a device that is most of the time in low power, and then it turns on, communicates with the satellite, and go back to sleep. If we are using GeoSatellite, my equipment may turn on. I will know that satellite is available, always available. I will communicate with the satellite, and I can go back to sleep. With LEO satellites, I need to know the orbit of the satellite, so I will wake up, and I need to know if the satellite, it's a moment, if I have a window of opportunity to communicate with the satellite, if it's available or not. And maybe the satellite is not passing that moment, so I will lose this window. I will need to wait for the next window to communicate. Also, beside the round-trip latency is very low in LEO, we have a catch here. Satellite operators for NTN are working the store and forward messages. So if my tag is located at this spot and satellite is here, I will be able to communicate with the satellite, but my message will not reach the core network yet. So this satellite, you need to travel until it get over the ground stations, then this message will reach the core network, and the satellite will exchange information with the ground station, and in the next passing over my device, the satellite can deliver my message. So for today constellations of Sateliot, for instance, they have 4 satellites, and the latency is expected to be about 8 hours to 12 hours, depending on the situation. With more satellites, with more ground stations, even with communication communication directly between satellites, this will improve. But the scenario today is latency very, very, very high for LEO satellites. From a commercial point of view, we probably will buy NTN connectivity the same way that we buy 4G or 5G connectivity. I will need to buy a SIM card, or I will have a contract with a network operator. So it's not different. And for who develop equipment like us, standardized solutions will enable us to choose the manufacturer of the module that we will use. So today we have modules from Nordic, from Quectel, from MediaTek, Qualcomm, a lot of manufacturers already providing modules for NTN. So this is good to the point of view of development. And also the tools are the same, the test process are the same. So a standardized solution may have its benefits. For our product, the convergence between terrestrial and non-terrestrial of the NTN is very interesting. For wildlife tracking, the animal may be in an area where I have coverage, or may not be an area where I have terrestrial coverage, so we can rely on non-terrestrial communication with the satellites. About the coverage and availability. LEO satellites can cover practically the entire planet, but the availability may be different from the coverage because of legal contracts, because of regulations. So maybe some regions of the planet, some countries may not allow that satellite communication that region. So it's not because we have a LEO satellite passing through all the planet that I will have connectivity in all the planets. So commercial decisions and licensing will define the service area that will be available. And for LEO satellites, also the availability will depend on the passes and the gateways. So this is impacting also in latency, as I said before. What we have seen today, NTN is the modules and development kits and access to the SIM cards are very new. And what we are seeing today is that not our module firmwares are compatible with every satellite operators. So today we may choose, if I use, for instance, Quectel, I will have some firmwares compatible with some satellite operators, not all satellite operators. So it's like, it is a standard, but it's not yet a full standard. I need to choose between the module manufacturer and the satellite operator that I plan to use. About the current coverage of LEO and GEO satellites for NTN, the picture here, it's the coverage, it's the footprint coverage of the Skylo that uses a Viasat satellite. This is a GEO satellite. The coverage you can check on this link if you want. So there is no coverage in entire Brazil yet. And in the case of the Viasat, the satellite is positioned about here. So it's not a very good location for coverage in Brazil. We have a not so good communication angle, visibility with the satellite. So in places with big buildings, we will have a lot of shade areas. And this is the coverage of the Sateliot network. They have 4 LEO satellites yet. This site is interesting because we can see the satellite coverage in real time. So we can see the satellites moving. In this picture, we can see 2 satellites here. So this is the footprint of 1 satellite. So compared with the GEO have a very big footprint, but this is a moving satellite and this is the stationary satellite. Now I'll talk about our marine tracking, the challenge that we have, and the NAVI project. NAVI program, it's an innovation program from ANP, National Agency of Oil and Gas. And it focuses on some offshore challenges that offshore companies have. Next Device is running one of these projects to tackle a challenge from Petrobras to monitor marine wildlife. So the objective of our project is to develop a low-cost, energy-efficient marine animal tracker using NTN communication, and to extend the battery lives also to using energy harvesting to collect energy from the environment and extend the battery life of the equipment. We have some important technology partners. We have the Inatel with the XG Mobile program. Also, we have Lactec with the Future Grid program. Petrobras, they are the challenge owner, and they are providing all the offshore context to us. And the Aquasis Research Group, they are providing to us all the conservation, animal conservation background, field operations, and will be through Aquasis that we will have access to animal in captivity to run the first tests. Because of the Inatel XG Mobile, we will be presenting this project in the 4 years from now fair in Barcelona. This show happens inside the Mobile World Congress. That's the most important communication show that we have. So it's all these partnerships are very important to the success of our project. Well, so why low cost is important and why high efficient is important? First, we have the scale problem. If my tracker is very expensive, as it is today, we cannot afford to monitor many animals. We will have a limited set of animals with trackers, and this may not represent the real behavior of the animal, just on individual. So for scaling, we need to reduce the cost of the equipment. For long-term operations, I need to have an energy-efficient equipment. This will define if my equipment will last days, months, or years, or multi-years in operation with the same single batteries on it. Also, the equipment must be must be easy to be installed, to be maintained by the field team, with field researchers team. So with solving the problem of scale, so if I have a very good amount of animals being monitored, if my device provides a long-term period of operation, and if I don't need to access this equipment while this is in operation, we can have a lot of data from these trackers. We can have data from long time of operation of these trackers, and we can really provide information for good understanding of the animal behavior and to provide information to protect this animal, protect the areas of these animals, and to plan offshore operations. Another challenge that we have is that how we will communicate using radio frequency with the equipment that may be underwater. So the water will attenuate the signal, so we can only communicate when the antennas are outside of the water. So we need to detect when we will have surface windows, when the animal goes to breathe. This will be a surface window where we can use the antennas to communicate and to acquire the GNSS signal and to communicate with the satellites. Also, I cannot rely on any kind of orientation of the antennas. I cannot rely on with the antennas with high directivity. So this is a very big challenge. I will have most of the time suboptimal link budget or communication with the satellites. And to help everything, we will have corrosion from salt water and also biofouling. So we have marine organisms being attached to the device. So it will compromise the antennas, tuning. Also, this will compromise all the sensors that we have in the equipment. So the marine environment is very, very complicated. About our tracker architecture and how we will do the NTN integration. First, before we start to develop the equipment, we need to understand what the requirements of the animal, the behavior of the animal that we will track. So this is the manatee. This is the peixe boi marinho, or West Indian manatee. They typically goes to the surface between 3 and 5 minutes to breathe. And each time, when you go to the surface, they spend only a few seconds breathing, and then it goes back underwater. So this will be our window of opportunity to communicate. And usually these animals habitat estuaries, rivers, and shallow coastal zones. Specifically, the West Indian manatee, it's more coastal zones, but the researchers often see animals like this going very far from the coast. So this drives some technical requirements that we have. So the communication windows that will be available will be very short, and this is a problem for NTN. I will show in next slides. So I will have the 5 to 15 seconds to attach and transmit. The GNSS location, it's okay to have 100 meter of precision. So with this time, I believe that we will get GNSS location with this precision. Data latency, it's okay to have a day or hours of data latency. So this is okay with the NTN network that we are evaluating. Operational life of the equipment, it's 12 to 25 months. So this is a very strong challenge. And because of this, we are using some systems of energy harvesting to try to extend the battery life. And the researchers also need some sensors, mainly animal behavior sensors like accelerometers, and to understand how the animal behaves. Also, we will implement environmental sensors and device diagnostic sensors. And then we have to deal with some trade-offs. I can choose between communication reliability and power consumption. If I need to have very reliable message delivery, so I send message to the satellite, I need to know that my end application received that message. I will spend a lot of energy because I will need to send message of confirmation. I will need to wait to message to really reach the end application. So this will drain my battery very fast. So we need to understand that I will not be a very reliable communication. Maybe one attempt to communication will fail, and this will be okay. The system must understand that this may happen. Also, the frequency and antenna size. We need small antennas, so this will also define what kind of satellite system we can use based on the channel that they are in operation. And we already choose so standardized solutions here, but one that is developing tracker, you need to choose between proprietary solutions like Iridium, for instance, or standardized like NTN. We are using NTN because we wish to evaluate the NTN in this kind of applications. Now a little bit more technical part. So this is our system architecture, our hardware overview. So this looks pretty much like any other IoT device. I will have a microcontroller, I will have an GNSS receiver, I have a communication module here, environmental sensors, antennas, and power management. What is different here from an ordinary IoT device is that I have a strong requirement of energy. This is why we are using energy harvesting here. And I will need to have a very strong firmware capabilities to understand, to monitor the power consumption of the device, and they need to know also the satellite constellation availability in case of LEO satellites. And the end-to-end system architecture is pretty straightforward. We will have a tag attached to a Manatee. This tag will send the message to the NTN satellite. The NTN will send the message to the terrestrial core network, and from the core network, we will receive this information, this data in our cloud platform. We are also developing this cloud platform to acquire all the trackers data and to make this available to the researchers. Of course, we can have the backward data flow here. So we will be able to send data from the cloud platform to the tracker. The power strategy that we are architecturing is to have a very aggressive dot cycling. The microcontroller will be able to shut down everything in the hardware. So we'll be able to shut down radios and sensors to save power. We will need to deal with GPS, GNSS or GPS optimization. We cannot rely on assisted GPS. So for every time, basically for every time that I will need to collect GNSS data will be a cold start. And this takes a lot of energy to get the first location point. Also, the NTN communication, the NTN specifications provide some features for power saving, like PSM in UETRX, but these features is not implemented in the satellites that we are testing yet. And I don't know if they will be implemented yet, because the way that device will use NTN will be basically attach and send the data and will be turned off. The device will not be connected to the NTN. And to help a little bit with the energy budget, we are employing energy harvesting systems to generate some energy. So this is the time that device will be in deep sleep. This is the GNSS acquisition. About half of the energy that we will spend with NTN attach and data transmission, and the consumption of the microcontroller and sensors is this part of the energy. Of course, this is an estimate, and we will measure this in field and also in laboratory. We are evaluating two communication modules, one from Nordic Semiconductor and another from Quectel. The Quectel, it's already with us. Nordic will get this module very, very soon. We have another variation that is not NTN, just narrowband IoT, but the hardware is the same. The Nordic also have an MCU inside the module that I can use to run my application if I wish. And we are doing we will do our trials with this module using the Satelliot LEO constellation. Nordic also partnership with other satellite operators, but we will try this module in this project with the LEO satellite constellation. The QuickTel, we have this development kit that we are doing some evaluating with it. And it does not have an open MCU here, so we communicate with this module using AT commands like any 4G or 4G or 5G cellular mobile model. And for QuickTel, we are evaluating the Skyle satellite, that's a GEO satellite. So with these both solutions in our equipments, we will be able to evaluate the LEO and GEO satellite orbits and choose what is the best for the final product. Well, the connectivity, the strategy of connectivity is very straightforward. We need to detect the surface event to know if the antennas are outside of the water. If so, we will perform a GNSS acquisition. This is mandatory to work with NTN. And then we perform the NTN registration, data transmission, and the equipment will back to sleep to save power. We have some trade-offs that we need to, this is the open questions that we have that we need to address. How many communications attempts we have done per day, for example. We need to manage message size, payload size versus frequency of communication. Also, if the communication does not happen, what the device will do, we will try again, or we skip, or we will store this information, or we will, I don't know, we may plan some strategies here. Also, the wake up agenda, to run this process, the interval to run this process may be influenced by the state of charge of the batteries. So if I have a lot of energy, I will perform less frequent communication, more frequent communication. If I have low power in my batteries, I can extend the interval of communication. And all these strategies may be different for LEO and GEO satellites. So this is an example of the AT command flow using the QuickTel BG95 and Skylo network. This is a simplified command flow. There are other commands that we have here, but this is the most important that I bring to you. So all starts with an AT command. I perform this AT command to the module to see if the module is responding. And this is the timestamp when the command was issued to the module. So here, I shut down the radio of the module, so just as a formal initialization, and I will set up the module with the satellite parameters. Here, I am telling the module that it must use the NTN connectivity, and I will adjust the band of communication. This is provided by the satellite operator. I will set the APN to Viasat. APN is just what we do with 4G and 5G modules, is the same. And here, I turn the radio on, and the module will start the attachment process. So here, I receive, this is a response, I receive the confirmation that the module is registered in the NTN network. It takes about 1 minute. And now I'm prepared, now that the system is attached to the NTN, I will perform a new UDP transmission. So this is a previous command that I provide to the module saying that I will send an UDP packet to this IP address. And here I send the message. This is an hexadecimal message that means echo. So when I send this command to the module will send the package to the satellite. The satellite will send the data to the ground station. The ground station send the message to an application that we developed that was running in the AWS. This application just replies the same message to the core network, then to the satellite, then we receive this message again through NTN network. And this took about 20 seconds here. So this is the time analysis. So all the process took about 1 minute and 28 seconds. If we disconsider the interval where the radio was turned on, 1 minute and 25 seconds. And after network registration, so only the payload flow, about 20 seconds. Remember that this payload flows until an end user application and goes back to the network. So this is one of the most important challenges that we have in this application, because as we see before, we have a communication window of about 15 seconds. That's the time when the animal goes to the surface. And I take 1 minute and 28 seconds to communicate, to do a registration and communication with the satellite. So we need to address how we will resolve this. So other open questions that we have, and that question will be answered with our prototype attached to the animal. So what is the probability of success of a communication that in real environment? How much energy each communication attempt to spend? How the motion of the antenna, orientation, and motion of the waves will impacting the communication success. And given the target battery energy that we will have, for how long the equipment will be in operation. And here we also will be able to measure how much the energy harvesting systems contribute to the extended life of the equipment. And then compare our lab-based power consumption with real deployment power consumption. And what this enables, what this technology enables. First, the scale of marine animal monitoring. If NTN hardware and NTN services costs were low enough to reduce the price of the device, this will enable more animals to be tracked. So this leads to a more information for conservation decision making. Also, all hardware, all infrastructure that we are developing in this project, a specific project, can be applied in other equipments for wildlife tracking or for communication in remote areas. And also we can give evidence-based conservation policy. So with strong, reliable data, this can lead to development frameworks, to conservation, and to evaluate or monitor offshore operations. So this is our milestone. We are currently here. We have done the product specifications, and we are now developing our first version of the schematics and hardware. In 6 months, 6 months from 3 months ago. So in 3 months, we will have our first prototype in the laboratory for tests in laboratory. And after this, we will also have the equipment installed in the animal. After 12 months, we will plan to have one device attached to the animal and providing data continuously. What we learned so far, some insights that we already have is that we have a very, the connectivity costs in NTN, it's still open. We don't have precise costs and also don't have the business model that will be practiced in NTN. We have uncertainty about the interoperability between modules and satellite operators, as I mentioned before. In the case of the Satelliot, there are few satellites, so the latency, it's very big, so we need to understand if this is okay for all applications. For the Viasat satellite, the position of the satellite is suboptimal, so we need to deal with some shady areas in regions with high buildings or or forest. Also, today it's kind of hard to get evaluation boards. It's kind of hard to get SIM cards for prototyping. I believe that will be improved after December. When other companies are launching development kits, but this point is still open. We don't have some point of contact to buy SIM cards, to buy connectivity in NTN. So that's it. Thank you very much. Thank you very much for the invitation to this talk. Thank you.
So questions?
Just for fun. Can you go back to the slide where you had these numbers for delays or whatever response time? Yes, exactly.
This one?
Yeah. So is this the processing time in terms of like latency to satellite and back? Or what do you mean by total processing time? So is this end-to-end latency time or what?
Yes, this is the first time that I
Start
the module,
and send it to
send the
satellite
data, yeah.
and then come back.
The data goes to
That's
my application and come back to the
That's
device.
called end-to-end latency.
Yeah. This is the geo satellite. This is the geo satellite. So
it's geo satellite, right? So that's my question. Go next to the slide. So when you go to the geos, the propagation delay is up and down. Just propagation delay is 271 milliseconds. I used to teach this since 40 years.
Yeah.
271 milliseconds. So now you have these 88 seconds or whatever. So do you encounter the end-to-end propagation delay or just without the propagation delay? Because the numbers don't match somehow. That's why.
We have 7
Is
milliseconds.
the question clear?
Yeah.
Clear?
Yeah. We have just for the communication, we have 20 seconds of the propagation delay. So this is
propagation delay is 271 milliseconds to geos.
Yeah.
So
milliseconds.
Millisecond, and then it's 20 seconds, you said.
Yeah.
If you convert it. Is it? I don't know. I'm asking you.
I don't know if I understand the question, but yeah, this is accounting for the propagation delay also.
Okay, good.
Other question?
Thanks for the presentation. It was really nice. And the project is extremely challenging. It's amazing how challenging that. And I have two questions. The first, it's a curiosity. So how Petrobras deal with the risk of this project? Because you show a very interesting approach that you have already set a lot of possible problems. And how Petrobras deal with this risk? Because it's really challenging. And the second one is regarding the practical setup. So you show a picture of the animal with a cord, and the sensor is there, or at least the transceiver for communication. And of course, the animal is swimming everywhere. So I think that cord will break at some point. So how to deal with that?
Okay, the first one, the project that we are developing, it's to solve a challenge proposed by Petrobras, but the project is not exclusively for Petrobras. So the NAVI program understands that this is an innovation project. So our commitment is to deliver a TRL6 product. So we need to put the tag on our product in the animal to do controlled tests. But it's an innovation project. So they understand that do we have our plans, we can reach our plans or not. Second question, this solution was developed by Aquasis. The attachment solution was developed by the Aquasis in Brazil. And they have a mechanism here that if this gets stuck in some way, they will release. So the animal will be free. So they have this concern to not harm the animal in any way.
More questions?
Thank you for impressive project. I'm curious to know, a LEO satellite move very fast.
Yes.
and it can create large Doppler shift and also synchronization issues. How we can reduce this issue? And the other one is the animal size can block the signals. And which antenna type is best for this? And what will be the location accuracy rate in your project?
The first question was about the synchronization to communicate with the LEO satellite.
Yeah, large Doppler shift and synchronization issue.
Yeah, we can acquire from the satellite operator the information about the location of the satellites. So when we acquire the GNSS information, I have a precise clock, so I can check when the satellite will be available. But when I start my module, I start the module with the scan feature. So they need to scan if the satellite is really there. And I will receive an OK of the module, then I will start the communication. I will have some minutes to do all the communication. So it's very narrow. I have a very narrow window of communication with the LEO satellite. We have not tested the communication with LEO yet. As I mentioned, December will be better because only in December there will be evaluation kits available from Nordic Semiconductor to evaluate the LEO communication. But it's how the information that we have, it will be performed this way. About the shading of communication, that's right?
Yeah. The signal blocked by animal size and shadow. Which antenna is best for this?
Sorry?
Because animal size can can block the signal. Which type of antenna is best for this?
Yeah. I don't know which one will be better, if LEO or GEO. The animal here will not block the signal because this antenna will be above the animal. We will not have this problem here. About the bad positioning of the Viasat satellite, GEO satellite, that we point our antenna in some angle. For our application, not be a problem because we are in the ocean, so will not be a problem. We will be able to communicate with the satellite anytime. In case of to use NTN in like a big center with a lot of buildings, the LEO satellites, as the satellite is passing, you have some way communication with the satellite, even if you have a large building near you, because the satellite is passing, you have the shady area will be moving to.
All right. And how much location accuracy you expect in your project? The location accuracy rate?
Because of the short time window, I can expect that we will be able to get a GNSS signal with precision of 50 meters or even better. But we are being conservative, so 100 meter to 300 meter will be okay for the application. But I believe that we will get better accuracy than this.
More questions? Okay, so let's thank Dr. Mazur once again. Thank you.
Thank you very much. Thank you.